the afternoon session, and have the pleasure to introduce Didina Serban, talking about twisting the pants, 3-point function of PPS twist operators in n equal to 2 Z2 twisted orbifold super Young mills. Please, Didina.
Yeah, thank you, Enrico. Thanks to the organizers for giving me the opportunity to speak here. So it's an ongoing project, ongoing, so unfinished, but still I think there are some nice features about this work that I would like to share with you today. So it's an ongoing work with Gwenael Ferrando, Gabriele Lefundes, who's a student here in the audience, Shota Komatsu, also here. So the motivation of this work is, well, so we would like to compute some simple correlation, three-point correlation function for very simple objects. And the motivation of this work is twofold. First, we would like to have some of the simplest wrapping correction to three-point function, a setup where we can study systematically the wrapping correction. And the other motivation is to look at the interplay of localization and the integrability, something that Kolya would call probably localizability. Because there are some results for these three-point functions which are coming from localization, and they look very much similar to what we see in object computed from integrability. So first I would like to say a few words about the theory that we are considering, because it might not be familiar to everybody. So this theory is the theory which is probably most closest to n equals 4 super Young mills. It's we twist the sphere, we twist the operators which correspond to the sphere. So the theory is obtained by from n equals 4 by twisting the sphere. So I will describe, I will try to show this briefly, how it works on the operators. We have the same operators as in n equals 4 super Young mills, the bosons, the fermions, the gauge fields. And the operators will be matrices of the size 2 times NC by 2 times NC. So I will introduce an operator which will be associated with the twist, which is the identity on each of the my identity and minus identity on each of the components of the gauge field. And all the fields are matrices 2NC by 2NC. So for example, the operator that we call Z will have a diagonal structure like Z0, Z1, so such that it commutes with the twist. So all the operators that we will work with will have a definite behavior under the Z2 twist. So this is Z2 twist. So this is true for Z and Z bar. And for the operators X, y, x bar, y bar, they will anti-commute with the twist. And all the gauge field and all the rest will have the same diagonal structure, which means that they have eigenvalue 1 under the Z2 twist. Of course, one can consider ZN twist. These are what are called quiver gauge theories, but for the moment, for the simplicity, I will just stick with Z2. So what does this twisting do to the supersymmetry of the theory? It just breaks part of the supersymmetry. So if for n equals 4, we have the symmetry given by PSU2, 2/4. So by twisting, we reduce the symmetry to PSU, SU2, 2/2 times SU2. So we are breaking part of the R symmetry, which is not SU2 or SU4 anymore. It's SU2 times SU2. So this is because of this action of the twist on the R symmetry, on the operators that are transformed by the R symmetry. And we still have the conformal symmetry is still here. We still have some symmetries, two supersymmetries, which allows, of course, to use localization to compute some of the supersymmetric objects in the theory. But let me now say a few words about the vacua of the theory. So, of course, the vacuum was before, the vacua were given before by Z to the L. Now we have the BPS operators, half BPS operators, which are given, there are two sectors. One is untwisted sector. These operators, I will call them UL, and they are given by trace Z to the L. So in terms of these matrices which are on the diagonal of the block diagonal structure of Z, we have trace Z0 to the L plus trace Z1 to the L. And the twisted sector of the BPS that I will call TL, this is trace of the same quantity but with a gamma inserted before taking the trace. So this will be trace Z0 to the L minus trace Z1 to the L. So the operators that I have mentioned here are this type of operators here. And one can do, so there are several things that are known from the point of view of integrability here. We know the spectrum, from the spectrum we know the asymptotic Bethe-Ansatz equations. So when you start to build excitations out of this vacua, so this was obtained by Beizert and Royban in 2005. There is a paper about the magnons called twisted magnons. by Gade and Rastelli. In 2010. And there is a recent paper on the QSC by XCSPEC. Yes. Yeah, I will take one from here. Yeah, I have to check the name. So this is a paper from 2023. But so for the things that we are interested in, namely correlation functions of these operators, unfortunately the spectrum cannot give us much information because the anomalous dimension of these operators is 0. So the information from the quantum spectral curve for these operators is not very useful. What I wanted to say also about the magnons, because we're talking about magnons here, is that the residual symmetry for the magnons will be given now by PSU 2 left times SU2, okay, let's call this right, SU2 times SU2. So this would be the left sector, which is, so the PSU2 symmetry in the left sector is broken by a twist, which I will now call, so this twist acts as 1 in the right sector times a diagonal matrix, which is 1 for the fermions and -1 for the bosons. So these are the first ingredients from the integrability. And we have from localization so using localization we can reduce the computation of supersymmetric quantities to quantities which do not break supersymmetry. We reduce them to matrix model, which was derived by Pestun in 2007, and there is also a work from 2016. Among the things that can be computed, there are the sphere partition function. So you put the theory on a sphere, and then you use localization. There, of course, this was obtained long ago using the localization, but I would like to cite 2 recent works which notice that this sphere partition function can be put in a particularly simple form. So there are an ensemble of collaborators. Let's say, so the 2 references are from one from 2021 and one from 2022. So they noticed that in the first paper that the sphere partition function can be written in terms of Bessel kernel, and in the second In the second reference, this kernel was recognized as an object that we know from integrability, and that I will introduce shortly. After the more or less in the same time, in the beginning of 2020s, also the two-point function of these BPS operators was computed by a group which contains Beccaria. So it's more or less the same people from experts of localization. Also there is a work by Michelangelo and Francesco Galvagno. Which give the computation of the two-point function from the localization and from perturbative computations. Also, there is comparison with holography, with results from holography at strong coupling. So the results are quite well understood and cross-checked. So the last computation which was done recently in 2022 is the three-point function of the same BPS operators. So it was obtained by Billo, Frau, Lerda, Pini. So I will give now the results of this computations. So let's first look at the two-point functions. So if one computes the two-point functions of the untwisted operators, so one obtains a result which, of course, depends on the dimension of the operators. And as I said, these operators have a dimension which is not renormalized, with a coefficient which is the one at zero coupling, which is L n to the L. So the correlation functions of untwisted operators do not receive corrections in the coupling constant, while the I think since I'm not writing very quickly, I think I left it here. It dries while I'm writing. So probably if I'm exchanging them from time to time, it's going to be better. Yeah, so twisted operators have the same space-time dependence, but with a constant here, GT, which depends on the coupling constant. So we have the usual identification of the coupling constant as in super Young-Mills. So I will write it as I will write the dependence in G. So G, this will be the zero coupling value times 1 minus the sum matrix element of some semi-infinite matrix that I will write shortly. So this will be, can be written as a kind of Fredholm determinant, which depends on the a parameter which is called L and which is given by the length of the operator. So this objects here will be something like this, the correlation function for the so that will be U bar L, UL, and here one has something like this. Well, should have a dotted line here also, TL bar, TL, and I can remember that here I introduced some gamma matrix in the trace. I do not represent the contractions, but I will just represent this operator here by some wiggly line in the two-point functions. So now what is this matrix here? I said that it's a semi-infinite matrix. So its matrix elements are given by some Bessel functions, 2m by times a prefactor. So, and some integral from 0 to infinity of, so exponential t 1 minus exponential t square times z 2n plus L of 2gt to m plus L 2gt. So this is what is, that's an object that will appear also in the next talk. It's a Bessel kernel. And it appeared in the study of the simplest four-point function that Frank proposed some years ago. So if you compute a four-point function with a lot of contractions here, so now I will draw the contractions. So you put these operators at some points in the space-time. Well, you do some conformal transformation to put 3 points at 0, 1, infinity. And then you have some, so you have plenty of contractions here. K goes to infinity, K goes to infinity, and here L. So this object can be computed by the method of hexagon decomposition. The method to compute correlation functions, the one, so one of the methods that are available for computing the three-point function. Well, the correlation functions. So this, because of this infinite number of contractions here, this object will factorize into pieces which we call octagon, which were called octagon. So this contraction here will give rise to this dotted line, and then the insertion of the operators will will be represented by some by these pieces of the spin chain, let's say, and then we have these L contractions between two of the operators. And you have the same thing on the other side of the of this figure. And this object was computed by summing of. So this is made by two hexagons. If we cut here the object along this bridge of length L, then you get two hexagons. And you can insert here a number of virtual particles, and you have to sum over the virtual particles in the in this channel. And if you are doing this, in fact, you are getting a kernel. The result is written in terms of the octagon kernel. Oh, that's not good. It's very thick. So K octagon with L bridge, in fact, will be this K at some particular value will be of the different parameters which enters into this octagon will be, in fact, our K L plus 1 here. So here we'll have to specify, for example, what are Z bar. So Z bar will go to 1, and the cross ratios for the R structure will be, sorry, not to 0, to 1, and this will go to -1. So if we take this limit here, we'll get the this kernel here. So this function, the function which multiplies the Bessel functions will contain in general the information about the kinematics of this object. So okay, now I can explain if it's not obvious why these two relations are equal. So you just compute the first element, first diagonal element of the matrix by defining. So this is the determinant of the minor of the matrix if you take out the first element, and you see that if you change if you chop the first line and first row and first column of the matrix of KL, you get KL plus 2 because of the structure of the matrix elements here. So this relation is already intriguing. Why the localization should see this object, which we know from the computation of the from the 4-point function. And the thing which is even more interesting is that the 3-point function also is written in terms of this kernel. So I think I will have to speed up a little bit. How much time do I have left?
15 minutes.
Okay. So for the 3-point functions, the ones that are non-zero, so the twist charge has to be conserved. So there is one which is non-zero, which is given by, so I take T bar here, I take T here, and I take U here. So all the function, the 3-point function that we can compute between the BPS have to be extremal, so P has to be equal to K plus L. And this object will contain some twist. And you see that because P is equal to K plus L, there is no contraction between these two operators. So this is non-zero, and there is another one which is non-zero, which is the one where you put T, L, T, K, and U bar P. So again, P is equal to K plus L. And now the twist goes from one leg to the other on the lower part of the diagram. So C, UK, TL, T bar P is equal to some value which is correspond to zero coupling, and then some function, sorry, C, CL of G, CP of G. So you see that only the legs with which contain a twist will be non-zero, and then we have TK, TL, U bar P, which is non-zero, and this is also some GK LP, which is the zero coupling contribution times CL of G, CK of G. And this function CL of G is given in terms of the 2-point function by this formula, 1 plus 1 over 2L. I'll try to change again the pen. So G dg log of G TL of G. And this, okay, I will write it here. This formula, okay, it's not very transparent as it is. So G is the one from this formula. So it looks like there is an identity which is non-trivial, which says that that is determinant of 1 minus K L plus 1 divided by square root of determinant 1 minus K L determinant 1 minus K L plus 2. Okay, so we want to understand this formula from the point of view of hexagon and 3-point functions. So let's, so how we recognize here something that is K octagon with L bridges. So now I want to compute this object here. This.
Sorry for not waiting. Is there an equal sign?
Yeah. Yeah. Sorry?
The formula we want to show is an identity between these determinants.
It's an identity between these determinants. I don't think it was known. Gwenel guessed it. We have partial proof of it. but it doesn't seem that anyone knew it before. So okay, so what is nice about this formula is that there is some factorization of determinants of Fredholm determinants. This is not a Fredholm determinant. This is a Fredholm determinant. So the rest of my talk will be an attempt to explain this formula here. So I will concentrate on this case where I will take k to infinity. So what becomes of this object here? I will get some object like this. So I will open this part of the pants because I don't want to care about it. And then now I have here I have my my bridge and my twist. So I have L lines here, the lines from these contractions. So what we see here, in fact, is nothing else than this object here, where I identified these two sides with 0 length. So this part here has 0 length. So I will cut open here. I will cut open along the twist. So what I get here there are two hexagons which are glued through this bridge of length L with the twist. So in fact, this part here is exactly the contribution of bridge magnons that come from the octagon. And then we have to compute the rest. Our hypothesis is that it comes from wrapping corrections, which are given by magnons on this mirror magnons on this side and mirror magnons on this side here. So the bridge magnons in this bridge will contribute 0 because I will try to just justify that these magnons are giving 0. Maybe not this one. Okay, I can erase this one, but not the other one. Okay, so now I want to do a computation of, in the last 5 minutes, to sketch what do we get when we have two magnons like this. On two opposite channels. So we'll take the prescription. So now I will have the two hexagons. Now I will open here this side of the operator. So these two pieces here are two pieces of these operators, and then I will put some. I will bring the magnons to the upper to one side of the hexagon. I will bring these two mirror magnons by gamma transformations to the edge of the hexagon, and I will compute the contractions among them. So I have to contract this like that, and then So that's the usual prescription of computing contractions of the mirror magnons. So here we are summing this. These lines mean that we are contracting. Sorry, that's supposed to be dotted. There are some directions on the lines, and the insertion of this twist here will appear by insertion of a twist before closing the line on one of the it was left in the left sector of the PSU22 PSU22 symmetry, but not in the other one. So now, if we are, and this also these magnons have some rapidity, which will be v u plus I epsilon u minus I epsilon v. So we want to shift a little bit the rapidity on, the rapidities on two opposite hexagons, because in fact the weight of this, the contribution of this magnons comes with interaction weight, which is given by u minus v plus I epsilon, u minus v minus I epsilon. So it's there is a second order pole divergence in the interaction weight of the two magnons as defined by the hexagon prescription, and this is equal to pi over epsilon delta of u minus v. So when we send this regulator epsilon to 0, this will normally diverge and will give in the case of normal wrapping in the 3-point function, this will give the renormalization of the energy. The will be a signal that there is some renormalization of the anomalous dimension. So in our particular case, when we are doing this contraction and this limit, we will if we contract this dotted line, we will get something which is like this, some two lines which contain some insertion of the twist, and here there is nothing. So this object will come with 1 over epsilon. This part here, and when we send u to equal to v, so this will be u, this will be v, and then we send v to u. So these two super traces will in fact decouple, because we can use here, we can use the unitarity of the S matrix. So this is schematically, this explains how to handle the matrix structure of the magnons. So this, in fact, by supersymmetry, it is 0, because it will be proportional in fact, to the decoupled. No, if I wanted to decouple them, so they are separated. So by supersymmetry, this one will be equal to 0. And then we have to expand in order to get the next term, we'll have to get to expand this combination of S matrices here. So we'll take the expansion in epsilon, and we'll get some derivative of the S matrix, which will be situated at some of the crossing intersection of these points. So this is a derivative with respect to U of S1, 2 of U and V, S minus 1 of 1, 2 of U and V, trace, and then we put U to V. So this object, we were able to guess what it is. So this is something which has a definite value, which is some object KA tilde of UU, which is the limit of some more general object that some kernel interaction kernel between magnons that we also are able to obtain in its particular form. So to explain what I have doing here is I compute the one magnon wrapping, and I get that there is no divergence in this one magnon wrapping, which is consistent with the fact that the anomalous dimension of my operator is 0, and then we get some correction, which is a finite part of this wrapping magnon, so which is given by some particular object, and then we were able to compute from this. When we have this, we can compute the one wrapping correction, which would be some over the bound states of some object which includes this kernel KAA times the weight which is associated with the bridge of length L that we have inserted somewhere there. So this KA tilde of UU. And if we compute this directly, this gives 1/2 of trace of KL plus 2, which is in fact the beginning of this expansion here in terms linears in K. So that's part of the answer. So now we are. I think I should stop. So what we also have checked is that wrapping and magnons, wrapping and bridge magnons factorize. So there is no cross term which combines these two contributions, and we are in the process of computing two magnon wrapping. So the result is encouraging. We obtain all the ingredients that we need to reproduce the next term there, which would be of the form trace KL square plus KL plus 2 square. It almost works, but there are some subtleties that we are still not yet understanding. But it looks promising that that we can reproduce this a little bit puzzling formula, because you see that the bridge contribution is factorizing nicely, but the wrapping has two different factors which factorize. So that's something that it's hard to have a physical intuition why it happens like this. So, okay, that was all that I wanted to say today. Thank you.
Thank you, Didina. Let's have one quick question.
No one else? Sorry, I missed the very beginning of the talk. Is
Yes.
there a connection between this and usual gamma deformation?
No, it's not gamma deformation. Well, gamma is the twist, but that's not gamma deformation. It's just a twist. So this is, if you want, you can introduce two different couplings for the two gauge groups. If you have the two couplings different, this is the theory that Eli Pomoni wants to show that it's integrable. I am at the point where the two G's are equal, and there it's just twisted n equals 4.
In the usual twisting of gamma deformation, I think it's hard to understand exactly where to put the twists, but here you managed to understand where to put the twists cleanly.
Well, it's a prescription, but it works. So the most important test is no correction to the energy. So in the case of gamma deformation, you should have a correction to the energy. So the twist will. You see that if you have a twist in both of these circles, there will be a contribution from both of them, and the divergence will be there, so you will have some correction to the energy.
Okay, so I have a quick question. Maybe it's for Ellie, but maybe, you know. So, is the dilation operator in this theory worked out at lowest loop as a spin chain, and is it integrable?
Here it's the same dilatation operator. You see, because you can move, you see that in the traces you can move gamma around because of this relation. So if you have you act with the dilatation operator somewhere, you can move your twist and you are safe. The rest is just n equals 4, usually n equals 4 action.
Thank you.
Welcome.
Let's thank Didina again, and we continue with Zoltan.